Welcome to day three. Day three, we're going to work more with derivatives, but today I'm going to show you something called the power rule. So after you're going to see this method, you're going to be like, why didn't I just learn this to begin with? Well, we have to do it, to develop the definition first before we can use higher level. So again, all names for a derivative, we're going to call things f prime, or sometimes y prime, or sometimes even dy over dx. So let's look at a basic function. F of x equals a constant, so it's just like f of x equals 5, or really y equals 5, which is a horizontal line. Well, right here is my nice y equals 5 horizontal line. So when we do the derivative, we're talking about slope. What is the derivative or the slope of this function? Well, definitely the slope of this function of every horizontal line is 0, or f prime is equal to 0. So my conjecture is, if I have a function that is a constant, 5, -2, whatever you want to call it, its derivative is 0. F prime is 0, or y prime is 0, or what we call dy over dx is 0. Let's look at other functions that aren't really that complicated. So a basic power function. A basic power function is a times x raised to the n power. That is what a power function is. So we did a couple of these last class, and we said the derivative of x squared was 2x, or dy over dx was 2x. And we also did x cubed. We said the derivative of x cubed was 3x squared, or dy over dx is 3x squared. Okay, is there a pattern to all this? Absolutely, there's a pattern to this. Okay, if you really pay attention, I see there's something's going on with the coefficients and the exponents. We'll talk about that in a minute. And it looks like the power, or the exponent, is down 1, or it's 1 less than before. Okay, it went from x squared to x to the first, x to the third, to x squared. Okay, so a polynomial function is just a bunch of power functions added together. So we had these examples last class. F of x was equal to 2x squared minus 3x plus 4, and we found the derivative was equal to 4x minus 3. And if g of x was equal to x cubed minus 5x squared plus 4x minus 7, we found that g prime, or its derivative, was 3x squared minus 10x plus 4. These were examples that we had from last class, and now I really see the pattern. The pattern is if I have a function, if f of x is equal to a times x to the n, well, then its derivative is going to be a times n times x to the n minus 1. So what we're doing here, we're doing coefficient times exponent, and then we're doing times x n minus 1, or we lose 1 degree on the exponent. It's not really that hard. All you got to do is multiply the coefficient and exponent, very easy, and subtract 1 from the exponent. So this is called the power rule, or I call it the shortcut rule. Instead of doing that whole f of x plus h minus f of x over h. So if my function is a constant number, its derivative is 0, and if my function is a power function, its derivative is here, where we have the coefficient times the exponent, and then raised to the x minus 1, where we lose 1 degree of the exponent. Let's try some examples. If y equals 1/2 x to the 4th, well, 1/2 times 4 is going to be 2x, and I lose 1 off the 4, it becomes x to the 3rd. So y prime is 2x to the 3rd. If f equals 5x cubed, 5 times 3 becomes 15, and x cubed becomes x squared, so f prime is 15x squared. And then finally, g of x equals 2x to the 6th. 2 times 6 is 12, and now becomes x to the 5th when I lose a degree of my exponent. That's how easy it is. It's not really that difficult. Now when I have a polynomial function, that is just a bunch of power functions added together. I just do one term at a time. So again, becomes 12, f prime is going to be 12x to the 5th, plus multiply this, 2x to the 3rd, multiply this, plus 15x squared. And this last term is a constant. And when I just have that, it is really going to just be plus 0. Because technically, 6 really means 6 times x to the 0. So if you did multiply 6 times 0, you do get 0. Let's try some of these. Make sure you do notation. And notation is that I need to see the f prime, or the g prime, or the y prime, whatever letter we're using. So again, this is going to be f prime of x is going to be negative 10x to the 1st. I don't have to write down the 1st. Multiply here, I get g prime of x is going to be 36x squared. Oh, this is a 1 here. So I have to do y prime is equal to negative 5 over 6 x to the 0, but I don't ever have to write x down x to the 0, because x to the 0 is just equal to 1. So it's just really y prime is equal to negative 5 over 6. These other examples, see, I have polynomials. I have to do one term at a time. F prime of x is equal to negative 15x squared plus 4x minus 8. And this g prime of x is going to be negative 12x to the 5th. Let's see. Multiply this, I get 12 over 2, or 6x to the 3rd. Do this, I get 15 over 6 plus 5 over 2 x squared minus a half. And that is the derivative of that function. Is the power rule any different when there's a fractional exponent? No. If y equals a times x to the n, then y prime is still going to be a times n, x to the n minus 1. I don't care what that exponent is. The exponent could be positive, it could be negative, it could be a fraction, it could be whatever, a decimal. It's all going to be always the same. So how do we subtract 1 from a fraction? Well, a over b is a fraction minus 1 is really a over b minus b over b. And as a result, I get a minus b over b. Okay, that's one way to look at it. Another way to look at it is top number over bottom number minus 1 is really going to be top number minus bottom number over the bottom number. Or better yet, numerator minus denominator over denominator. Let's look at an example. 5/3 minus 1 is really 5/3 minus 3/3, or I'd rather just do top number minus bottom number, which is 2 over 3. Or we could do negative 3 over 4 minus 1, and the top number is negative 3 over 4, so that would be negative 7 over 4. And the whole key to this is that the denominator will not change. So that's how I subtract 1 from a fraction. I just do the numerator minus denominator over the denominator. Works every single time. It's never going to let you down. Let's try some examples. F equals 4 times x to the 3/2. 4 times 3/2 is 12 over 2, which is 6. and x. 3 halves minus 1 is 3 minus 2, 1 over 2. Negative 12 times 1/3 is going to be negative 4, x. Numerator of 1, 1/3 minus 1 is 1 minus 3, which is negative 2/3. And then this last one, well, it doesn't really reduce, so I get negative 10/3. I have x, negative 5 over 3 minus 1 is negative 5 minus 3, which is negative 8 over 3, so y prime is equal to negative 10/3, x to the negative 8/3. That's all it is. Okay, same rule that we did before, what I call the power rule or the shortcut rule. Doesn't change because I had a fractional exponents. Coefficient times exponent, and then subtract 1 from the exponent. So how do we handle functions that look like this? F of x equals 4 over x cubed, or g of x equals 6 times the square root of x. Well, the key is you have to rewrite them so they look like power functions, and they have to be in this form. I only could use this power rule, shortcut rule, if my function is in the a times x to the n form. So I'm going to have to rewrite. So again, you need to remember your rules of exponents. Something with, if you have a function with x in the denominator, it becomes x raised to the negative exponent. So 5 over x squared is really 5x to the negative 2. And when we have roots, they become fractional exponents. So 3 square root of x is really 3x to the 1/2. And when we have power and roots, the numerator is the power, the denominator is the root. So if I had something like 4 cube root of x squared, it becomes 4x to the 2/3. Okay, so things like that. So let's try some examples. So first, I should rewrite these. So for all these problems, I'm going to rewrite 4 over x cubed is really 4x to the negative 3. And now I could take its derivative by using my different power rule, negative 12. And don't forget, it's subtracting 1, so it's x to the negative 4. If you want to rewrite this as negative 12 over x to the 4th, that's fine, but I would just leave it as negative 12x to the negative 4. I rewrite this as 6x to the 1/2. I multiply, I get 3x 1 over 2 minus 1. Top minus bottom is going to be negative 1/2. So d prime is 3x to the negative 1/2. I rewrite this as negative 2x to the power of 2 root of 3. I multiply, I get negative 4/3. And when I subtract 1 from this exponent, 2/3 minus 1 is top minus bottom, negative 1 over the denominator of 3. That does not change. And this last one, where it gets a little bit trickier, it's going to be negative 5. And this is x. It's in the denominator, it's going to be a negative. The power is 3. The root is 2. So it becomes negative 5x and negative 3 over 2 is the original function. Now when I take its derivative, I multiply. I get 15 over 2. X. Top number minus bottom number is negative 5 over 2. And that would be its derivative. So this last problem I'm going to rewrite over here. So g of x is really 2x to the power 3 over 4. Minus 6x to the 2/3. I don't have to rewrite that. It's already given to me. Minus 9x to the negative 3. Plus 5x to the 4th. Minus 10. And now you can take its derivative. Multiply here. I get 6 over 4, or 3 over 2. X. 3 minus 4 is negative 1/4 is my exponent. Minus, that gets 12 over 3, or 4x. 2/3 minus 1, or 2 minus 3 is negative 1 over 3, plus negative 9 times negative 3 is positive 27. Subtract 1, I get x to the negative 4th. And then when I multiply here, I get plus 20x, subtract 1/3. And here's my little constant, and the derivative of my constant is always 0. So this is my final derivative right there.